Just a second. Okay, let's get started. So good afternoon, everyone. How are you doing? It's good? Good? Okay. So before starting, take a look at the schedule a little bit. So we will continue logical database design. We are June 13. Then how many? Yeah. And then this Friday is our due date of assignment 5 and the discussion 5. So please keep in mind the due date. Then submit your work. After that, we just a couple of weeks, the end of the semester. Yay! So 2 more about the physical database design here. Okay, and then last assignment 6 and the discussion 6. Then Thanksgiving week. After that, so yeah, important thing is final project. The final reflective assignment due date is November 30th, the last day of November. Then soon course evaluation is December 3rd. So that link, student course evaluation link, will be sent to you on my MGA email, I think, from the MGA. Okay, that's it. No, we don't have we don't have the class. No class. So usually the last lecture every semester, I don't have the class. So focus on the final project or the final assignment. So, okay. So including today, we have just 3 classes. Today, next week, the following, the 3 more, okay? So that's all about the schedule, okay? And then before continuing this one, just to remind you, so normal form, normalization. So normalization is to process a relation into the normal form. So we have first normal form, second, third, BCNF, voice code normalization form, and then fourth. Okay, so if you have a relation, if the relation is in first normal form, those 2 conditions satisfied. First, that table should be a relation. To be a relation, total 8 conditions are satisfied. That's one condition for first normal form. Second, a relation must have primary key. That's all. Relation and primary key. That table is called in first normal form. Make sense? And then what is the second normal form? 2 conditions. One is that first in first normal form, and then the second condition is all non-key attributes are determined by entire primary key. That means here you have a relation R, capital R, and there are 5 attributes A, B, N, or P. So the composite key AB is a composite primary key, and the N or P are non-key attribute. So N or O or P should be determined by the entire primary key, A and B. N or P is determined by part of the primary key, A, or the B. It violates this condition. So it is not a in second normal form. Make sense? Christina? Okay. And then third normal form is relation should be in second normal form and no non-key attribute determined by another non-key attribute. For example, A, B are entire composite primary key and N, O, P are non-key attribute. So if okay, non-key attribute NOP should be determined by primary key. If N or O or P can determine the other non-key attribute, it violates the third condition. Okay, so this is a third normal form. And BCNF, the relation should be in third normal form, and then every determinant must be a candidate key. Okay, that is a condition for BCNF. So last week, we take a look at this example, student advisor example. Then we will continue with other example. So think about if you have those kind of table, student activity, there are 5 columns, student ID, name, activity, activity fee, amount paid. So can you find functional dependency from this table? What kind of functional dependency exist in a table? You know that functional dependency is A, like B is determined by A, or A is a determinant of the B. Activity, okay, activity determines activity fee. Okay, so golf 65 and the golf 65, swimming 50, skiing 200, skiing 200. That's right. Activity determine activity fee. This is the first, the functional dependency. And anything else? How about student ID? Student ID can determine what? Student name. Okay, student ID determine student name. Okay. How about activity? Student ID can determine activity? No. Why? For example, 100 is associated with the multiple activity golf and skiing. How about the activity fee? No. Why? 100 is associated, 65, also 200. So multiple values are associated. How about amount paid? 65 and 0, associated multiple. So only student ID determines student name. And also activity determine activity fee. And one more. Can you find it? One more. like treasure hunting, right? Student ID and then activity. Student ID and then activity. Oops, not student name. D and the activity and determine what? Activity fee. And also the activity determine like request activity fee. And also amount paid. Student ID activity also determine amount paid. So makes sense, right? And then here, think about that. Activity determine activity fee. Student ID and activity is a composite determinant. Determine what? Activity the same thing. But we here unnecessary column is added in this case. Only we know if we know the activity fee can be determined. So we don't know student ID. This is like a redundant. Okay, so can oops, remove this part. Only student ID and activity can determine amount paid. So how many functional dependencies are there? 3. So these are the original table is not in third normal form. So we have to normalize. Normalization means split. Okay. Like that. We can split into 3 relations. One is that student relation table, activity table, and then can name it, for example, payment table. So student ID determines student name according to this functional dependency. And activity determine activity fee, second. And then student ID and an activity determine amounts paid. So we are able to split the original table into the multiple table, the 3 tables. So in this case, like that. So each tables are, for example, this is a primary key. It's like only one candidate key. Candidate determinant. Determinant must be a candidate key to be in the BCNF. So student relation is in BCNF. And also, this is a one determinant, one candidate key. So it also in BCNF. And this one is the same. Okay, so if the given table is given, we have to think, first of all, we have to find functional dependency and then split to normalize. Why we have to normalize? There are 2 purposes. One is that the purpose of the normalization is to remove anomaly, like insertion anomaly, deletion anomaly, and update anomaly. This is one. The second is reduce redundant data in a table. Okay, so this is the goal of the normalization. Make sense? Okay. So the next one, multi-valued dependency. So a little bit different concept. So in a functional dependency, we only think one column must determine the other column. In that case, if the values of B is multiple values in a B column is associated with one value of column A, column in the A relation, we can say that there's no functional dependency. That means here, okay, so student ID and then activity 100 is associated with golf and also associated with skiing. The multiple values are associated. In that case, there's no functional dependency. But the other concept is multi-valued dependence is a determinant. This match is associated with a set of value. So one determinant is matched the multiple value. There is a multi-value dependency. Okay. Now this is a functional dependency, and that one is a multi-value dependency. So for example, employee name, degree, name, sibling, heart kit name, heart. Take a look at this table. So there are three tables. The first one, employee and degree. Name and then degree. For example, Green. How many degrees he has or she has? 3. BS, MS, and PhD. It makes sense. And Jones, associate, and bachelor, AA, BA. Okay. How about employee and then sibling? Jones has a 3, sibling, Frank, Fred, Sally, for example, like that. So sometimes when you combine those two tables into one, we can make this kind of table. For example, Jones has a 2 degree and then 3 sibling, like AA, BA, Frank, Fred, Sally. So AAA, Frank, Fred, Sally. BA, Frank, Fred, Sally. So when you combine how many rows are we have to create? Total 6, right? Something weird. But assume that the Jones owns another degree, MBA. But in that case, we have to insert 3 rows. Jones, MBA, Fred. Jones, MBA, Sally. Jones, MBA, Frank. We just want to add one MBA degree, but the table, 3 rows are added. That is update anomaly. Okay, so those kind of multi-value, the dependency are in case of multi-value dependency, the process to normalize is called the first normal form. So 1, first normal, second, third, BCNF, side related to functional dependency, one-to-one matching. But multi-value dependency relate to the false normal form. Okay. So same example almost. Okay. So again, with the simple example. So to be, if a relation in false normal form satisfies two conditions. First, that relation must be in BCNF. And then another one. No non-trivial multi-value dependency unless A is a superkey. The different terminology here. And before that, multi-value dependency can be represented by double arrow, like that. So these double arrows means this is a multi-value dependency. So you have to consider the false normal form. Okay. So, and then there's another terminology, superkey. The superkey is a set of attributes that uniquely identify rows in a table, but may contain unnecessary attributes. So, a table, we are able to find the candidate key. Maybe several candidate key we can have. This is a set of candidate key. Okay. But superkey means unnecessary columns, maybe student ID and student name. The composite is a candidate key for this table, this relation. But maybe you can add some SSN, something like that. So that student ID and student name is a candidate key, but sometimes if you add unnecessary column SSN, so create another key that is called the superkey. So the superkey is a superset of, this is a superkey, this is a candidate key. So candidate key is a subset of superkey. Superkey is a superset of the candidate key. So definition of terminology. Make sense? Then, so what is non-trivial? The meaning of the non-trivial. So non-trivial multi-value dependency here can cause redundancy or unnecessary data combination. Okay, let me show the example. And then non-trivial means, okay, so this is condition. This multi-value dependency A to B is non-trivial if two conditions are satisfied. One is that B is not a subset of A, and then A union B is not equal to the total the set. If the relation is R and then consists of A, comma, B, and C. So A, this is a column. Column A union B is not equal to R, that condition. Okay, so this definition is a little bit academically, so a little bit confused to understand, but I'd like to have the example, the table. So think about this table. Student ID, course, and hobby. Okay. Student ID 101 and register math and science. the multiple courses. Makes sense. The Christina, you can register the multiple the courses like database and then software engineering, security, whatever. And also you can have so multiple hobby, chess, the music, like that. Okay? You can create those kind of table. So think about that. So if you have a table, we have to find the determinant. From the determinant, we determine candidate key. From the candidate key, we determine primary key, right? So student ID can determine course. What do you think? ID 101 is associated with only one value in other attributes? No. Why? 101 is associated math and then science. So the student ID cannot determine course. No functional dependency between student ID and course. How about student ID and their hobby? Student ID can have the chess and the music. So multiple values. There's no functional dependency here. Okay. How about student ID and course? Composite key. Student ID and then course can determine hobby. What do you think? No. 101 math is associated chess or the music. The multiple values are associated. So also student hobby cannot determine course, vice versa. I connect the power. Okay. How about this one? Student ID and then hobby can determine course? No, it has math and science. So there's no functional dependency in this case. Okay. So to uniquely identify each row, we have two composite key with three attributes. Student ID, course, and then hobby. ID like that. Okay, but just something weird. There's no non-attributes, the key. We need all the columns to be a primary key determinant, right? So in this table, no non-key attribute. Student ID, course, hobbies are composite entire key. Then that's why partial dependency and transitive functional dependency are not exist. The partial dependency is from second normal form, and transitive functional dependency is from third normal form. But we don't have non-key attribute. So this one and this one, those functional dependencies are satisfied. That means this table is third normal form. Weird, but according to the definition, that table relation is in third normal form. But there is an anomaly. For example, if you add the physics to this table, 101 register physics, how we have to add rows. 101 physics, chess. 101 physics, music. We have to add two rows, right? That is a update anomaly. But this is a third normal form, but update anomaly exists. So we have to remove that anomaly. And so, but there's no functional dependency, but there are multi-valued dependency. Student ID, multi-valued dependence on course. So student can ignore multiple courses. Math, science is unlimited. The set of in the definition of functional dependency it's here. Set of possible value. Not this one. Set of set. So if the value of A is same, set of values for B. In this case, 101 can ignore math, science, physics. It's a set, so limited. And also, student ID can have chess and the music or hiking. It's a limited set, limited number of sets, not unlimited. So can have the multi-value dependency like this. Make sense or confused? Okay. 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 So then here, so non-trivial means B is not a subset of A. Think about that. This is A, and then this is B. Student ID, course, A and B. It's a multi-value dependency. So B is a subset of student ID. You can say that? No, student course is not a subset of student ID. It's an independent. Or student ID and hobby. Student ID and hobby. This is A and this is a B. B is a subset of A? No, B is not subset of A. This is a one, the condition to be a multi-value dependency, non-trivial, this one. Okay. And then the other one, the union of A and B now equal to set of all attributes in the relation. Here, this is A and in this A and student ID course A union B R is student ID, course, and then hobby. So student ID union course is equal to all set? No. Or student ID union hobby is equal to total set? No. So it satisfies this condition. So see. That's why this relation violates first normal form. So how we split this table like that, the composition of into the first normal form. Student ID, what is it? Student ID, and then course, and student ID, and then hobby. Okay. So if a table, if a relation has a multi-value dependency, we have to split independent columns. student ID course, student ID, the hobby. Make sense? A little bit? Okay. Life. So that is a fourth normal form. But if you know maybe the fifth or sixth or high order of normal form, but they are very exceptional case, so the rare case. But if you know first, second, third, BCNF, even fourth normal form, we are able to normalize the table to design your database. Make sense? Okay. Then next, let me see. Types of database. So what kind of the database? Roughly, can you see? Updatable database and the read-only database. What do you think? What is a read-only database? Yeah, so read-only just read. We don't update the value into the database. And updatable is a normal database. We send the query and then update the value and then retribute and the delete and the drop and so on and so on. Okay, so for updatable database, we need tables in the BCNF. Okay, every candidate must be every determinant must be a candidate key. For read-only database, we don't need BCNF table. Okay, depends on the business environment you can design, which the design is better performance in terms of the performance you have to think. Okay. Then update of database. Okay, if you are constructing updatable database, we need to concern about modification anomaly and inconsistent data. So for those things, we need normalization, split table. Okay, this is for updatable database. Then there's a one terminology OLTP. Okay, so I have short video about a second. You cannot see. It. Sorry, the Gregory Macon campus. Can you hear me? I unmuted. Can you hear me?
OLTP are often confused with one another. So what's the difference? Analytical and transaction, as in online analytical processing and online transaction processing. That's it. That's the difference. But don't go just yet. I have 3 boxes to fill because when it comes to using data to make smarter decisions, it's not a question of choosing between OLAP and OLTP. It's a question of how to make the best use of both processing types for your situation. Within the data science field, OLAP and OLTP are 2 types of data processing system. One uses data to gain valuable insights, while the other is purely operational. So let's start by defining OLAP, or online analytical processing. And it's a system for performing multi-dimensional analysis at high speeds on large volumes of data. And where do these large volumes of data come from? They're typically from a data warehouse, a data mart, or some other centralized data store. OLAP is ideal for tasks such as data mining, business intelligence, and complex analytical calculations. And it's also well suited to business reporting functions like financial analysis, budgeting, and sales forecasting. Now, the core of most OLAP databases is the OLAP cube. OLAP cube. Beautiful, isn't it? The OLAP cube allows you to quickly query, report on, and analyze this multi-dimensional data. And what is a data dimension? Well, it's simply one element of a particular data set. So, for example, sales figures might have several dimensions related to region, time of year, and product models. And the OLAP cube extends the row by column format of a traditional relational database schema and adds layers for other data dimensions. So, for example, while the top layer of the cube might organize sales by region, data analysts can also drill down into layers for sales by state or city or a specific store. So that's OLAP. What about OLTP? That's online transaction processing, and it enables the real-time execution of large numbers of database transactions by large numbers of people. OLTP systems are behind many of our everyday transactions, from ATMs to in-store purchases to hotel reservations. OLTP can also drive non-financial transactions, including password changes and text messages. In fact, my very first job involved working with an OLTP system. OLTP systems use a relational database that can do a bunch of things. For example, process a large number of relatively simple transactions. For doing things like insertions, updates, and deletions to data. And to do this with rapid processing, with response times measured in milliseconds. They also enable multi-user access to the same data while ensuring data integrity and provide indexed data sets for rapid searching, rapid retrieval, querying. So OLAP does all of the infrastructure work. Important stuff. It's just not as pretty as that OLAP cube. Okay, now can you see how we can combine these two? In reality, many organizations will use OLTP systems to provide data to OLAP. And that's the difference between them. OLAP is optimized for conducting complex data analysis, and OLAP systems are designed for use by data scientists, business analysts, and knowledge workers. OLTP, on the other hand, is optimized for processing a massive number of transactions. OLTP systems are designed for use by frontline workers like cashiers, bank tellers, and hotel desk clerks, or for customer self-service applications. Choosing the right system for your situation depends upon your objectives. Do you need a single platform for business insights? OLAP can help unlock data from vast amounts of big data that you have stored. Or do you need to manage daily transactions? OLTP is designed for fast processing of large numbers of transactions per second. If you need to do both, well, most of the time organizations use both OLAP and OLTP. In fact, OLAP systems may be used to analyze data that leads to business process improvement in OLTP systems. And ultimately, yes, also create more of those fancy looking cubes.
Can you have the concept of the OLTP and the OLAP? OLTP system, so we need what kind of database? Updatable database. Okay. To make updatable database, we have to normalize. So usually the BCNF normal form we need. Okay. Is unmuted. Okay. Then, so again, the advantage and the disadvantages of the normalization. That said, normalization can remove the anomalies and then reduce redundant data, duplicate data.
So basically, if you're analyzing like a big sales funnel or something,
yeah. So, yeah. So using the OLTP system, we get a lot of the data. And then after the data we collected, then all that system analyze. For example, Nicole, what kind of the grocery she usually buy? Or the Joshua, what kind of car you're interested in? And according to those kind of data you derive, maybe the marketing department send the email, targeted the mail, something like that. Or they can create the coupons, the targeted coupons. Okay. But this advantage of the normalization is more complicated SQL for multiple subqueries and joins. If we have just one table, it's enough to have one single the SQL statement. But if we multiple table like that, we have to join to find the correct the data. Join. But in terms of the performance, if we have the multiple join operation, the performance will be decreased. Okay, so that is disadvantage of the normalization. Then, okay, so that is updatable database. And so, okay. Sometimes we just need the read-only database. So, for example, that case, think about this example, customer table. There are how many? 1, 2, 3, 4, 5, 6, 7. The columns, customer ID, last name, first name, street, city, state, and then zip. So first of all, we have to find functional dependency. So for example, custom ID determines names, streets, and city, state, and then zip. And also the zip codes can determine and city and state. So we can split like that. Customer to table and then zip code table. Think of the zip codes. How often the zip code is updated? Almost never, right? Maybe 100 years or 200 years. But if a new house are added, is built, in that case, we can add. But if the zip code is fixed, we don't modify, right? So like this kind of the zip code, we don't need updatable database. Just read-only database is enough. But for read-only database, in a read-only database, we don't need the BCNF normal forms. Maybe just the whole, or the single table is enough. Why? In terms of performance, one single table has a better performance. So this is a example of a read-only database. And then I have another maybe read-only database, commonly used data warehouse or data lake or data mart. Okay. So I have another video. Is
What's going on, everybody? Welcome back to another video. Today we're going to be taking a look at the differences between a database, a data warehouse, and a data lake. First starting out, I had only ever heard of a database. I think that's what most people are familiar with. But I had never heard of a data warehouse or a data lake. And so in this video, we're going to be walking through the differences between each one of them, as well as how they kind of connect with one another. So let's jump onto my screen and get started. All right, so we're going to be taking a look at a database, a data warehouse, and a data lake, but let's start with a database. Now, when someone says a database, typically they're referring to a relational database. Now, a relational database can capture and store data via an OLTP process, which stands for online transactional process. So when a company completes a transaction and sells an item, it'll record that within a database. And that data has the ability to be live, real-time data. Data in a database is going to be stored in tables, which has columns and rows, and to be highly detailed, which means you're going to be able to go in and see every single aspect of the data. And databases also have a really flexible schema, which means you can go in there and kind of change things as you go to make it work for what you need. Now, a data warehouse is also a database, just like we were looking at before, but it's going to be used for analytical processing, or OLAP. OLAP stands for Online Analytical Processing, and it's created to basically analyze huge amounts of data. Now, if you notice on the last slide, there were these three databases, and they were just kind of sitting there, and they were storing the data. In this visualization that we have on the right, these three databases on the bottom are all aggregating and sending their data to this data warehouse via an ETL process, which is where it extracts the data, it transforms it, and loads it exactly how they need it in this data warehouse. And that's how data is put into the data warehouse. It isn't getting it directly from the source, but it's being put into a database, and via the ETL process, it's being updated as it goes or whenever the ETL process runs. A data warehouse will always have the historical data, but it won't always have the current data unless the ETL process is running every single day or very frequently. The data in a data warehouse is also a little bit different because we're doing this ETL process to get the data in there. We're not actually putting every single piece of data or every column and row in there. We're typically summarizing it and then putting it in there, which will allow us to process that data for our analytical purposes much faster. Now, a data warehouse is going to have a much more rigid schema, so you really need to plan ahead with how you're going to put your data into a data warehouse. It's not as flexible as just a database. So now let's look at some of the key differences between a database and a data warehouse. A database is going to be used for recording transactions, or a data warehouse is going to be used for analytics and reporting. A database is going to have fresh and detailed data, where a data warehouse is going to have summarized data. It's only going to be as fresh as the ETL process is created. A database is going to be a little bit slower for querying large amounts of data. And when you do query large amounts of data, it can actually slow down processing all those transactions. A data warehouse was designed for the exact opposite. It was designed to be very fast at querying and not slow down any processes, because it isn't part of that transaction processing call. So now that we've looked at a database and a data warehouse, let's take a look at a data lake. A data lake was basically designed to capture any type of data that you could possibly want. It could be a video, a picture, an image, a document, a graph, anything you can imagine that you'd want to put in a database or store in some way, you can store it in a data lake. Now, there are a ton of use cases for a data lake, but I think people who work with machine learning and AI get to use it or benefit from it the most. They can use all that structured and unstructured data and create models to really use it in its raw form. Where if you want to use it for analytical purposes, typically you're going to have to clean it up a little bit, do a little bit more work to actually make it useful. And so a data lake is just that. It's this lake where you can basically throw any type of data in there, but it's not always super useful because you're just putting it in there in its raw form. If you want to use it for analytical purposes and reporting, most of the time you're going to want to clean that up and put it into a database or a data warehouse. So now when we're looking at all three, they are all different and they're all used for different purposes. So no one option is better than another for your data. If you're using it just to record transactions, a database is what you should do. And if you have a large amount of data that's just too much for your database to handle, it sounds like you might need a data warehouse. And if you have all of this data, you have no idea what to do with, or it's unstructured, it's semi-structured data that can't fit into a database, well then I highly recommend using a data lake. There really is no one size fits all. All three of these can be options for different uses. And in fact, you can use all three within one company for just different things that your company needs. So I hope that that was helpful, learning the differences between a database, a data warehouse, and a data lake. Again, I had really never used a data warehouse or a data lake when I first got into analytics. But now that I've gotten a hands-on experience with all of them, they're all really interesting to be used for so many different things. So thank you.
Okay, that is a very short explanation of the data warehouse. Okay, data mart also, and the database. So I hope that those two videos are helpful to understand the difference between the terminologies. Okay. And then see read only. Okay. In normalization, it will be discussed about physical database design. Okay. And the last one I'd like to have today is the procedure. Okay. So do you remember these steps? Maybe the first or the second class I mentioned about the steps. First of all, if you want to design your own database, first of all, we have to do conceptual design. In other words, conceptual schema based on ER relationship, entity and relationship diagram. Do you remember the ER diagram? Something like this, right? After finishing conceptual design, we have to do logical design. Logical design includes normalization, and then write a statement using SQL. So actually create the tables. Next one is a physical design. Physical design, so we'll discuss next and the following week. Okay. So this is a steps. Maybe is transform a data model into a database design. So first, create table for each entity, create a relationship, and specify logic for enforcing minimum cardinality. So here, create a table, and then we have to select primary key, or just in case, the alternate key, and also specify the property of each column in a table. So no status, data type, default value, and data constraints, and then do normalization. Okay. After that, we create relationship between entities, one-to-one, one-to-many, many-to-many, the binary or unary or ternary, depends on the business environment. Okay. And then add cardinality and the modality. Okay. So this is a procedure. This kind of things we already mentioned. And then the last one I'd like to talk is the data types. So when you design the table, that you select the columns, student name, student ID, address, first name, last name, SSN, MJ ID, and so on and so on. What kind of data type can you use? So this is a SQL Server, like this, that, this. How many data types? It's a lot. So depends on your requirement. We can choose the correct one. Time, you can select the time stamp with the time or the timestamp with time zone. And then interval year to month and day, or just a simple date. Or if you want to select the type for what else? SSN, maybe integer or a string character. What kind of character? The fixed size character or variable length? It's up to you. You can design this. So take a look at this, the PPT, the later when you actually design your database later. Okay, be helpful. Yeah. So that's all today that I have. Maybe so 10 minutes, but today I'd like to call it a day a little bit earlier. Okay, if you don't mind. Any questions so far? Perfect or nothing? So if you have any questions, just let me know what to send the email. Okay. Thank you, and then have a good evening, and see you next week. Okay.